Thank you for letting me up. So the speaker today is Junghoon. He's from Seoul National University. He's in National National Lab. Nothing like quantum machine learning research. So usually we investigate the generalizations of variational quantum circuits and also the verification the computing. So today's talk will be about addressing the current challenges in quantum machine learning through molecular ensembles. So let's look at the speaker.
Thank you for the introduction. I'm Junghoon Park, and I apologize for being late for the delay, and thank you for your patience. So I will start the presentation. So for those who might not be so familiar with quantum machine learning, I will briefly introduce what it is. So quantum machine learning, QML, are algorithms that leverage the principles of quantum mechanics to process and analyze data. So it's basically machine learning algorithms that are based on quantum mechanics that uses the principles of it. So, and variational quantum circuits, which is also called as quantum neural networks or parameterized quantum circuits, these are the quantum equivalents of neural networks in classical machine learning. So the basic structure of VQCs are shown in the diagram on the right. So there are, in large, 3 different parts. There's a feature map, which encodes the classical data into quantum states. And then these quantum states are processed through the variational quantum circuits, which are composed of unitary matrices, unitary gates. And then after the quantum states are processed, they are converted into classical outputs using the measurement circuit, the measurement layers. And then using the classical outputs, the entire quantum circuit model is optimized using the classical optimizers such as gradient descents, atom optimizers, and so on. So this kind of VQC, it is inherently kind of hybrid because it uses the classical optimizers, and while the model is processed using the quantum circuits composed of unitary matrices. Okay. The current challenges of this QML, quantum machine learning, is shown as follows. There are a lot of challenges. The first one would be related to hardware. There are a lot of the quantum hardwares have a lot of noise. There's decoherence, and these noise and decoherence leads to quantum error, which means that the output deviates from the ideal quantum outputs. So it will be a lot of incorrect measurements and outputs that we get from the QML algorithms. And also there are hardware constraints which makes the number of physical qubits that we can use to be very limited. And also it is hard to make a quantum circuit that has a high level of connectivity, which means that the number of qubits that we can use is limited. Also, the connection between the qubits could be also limited as well, which means that it is very hard for us to make a large quantum circuit composed of a large number of qubits and very sophisticated connection between them among the qubits. And also, it is difficult to train a quantum circuit because of barren plateaus, which would be equivalent as vanishing gradient problems in classical machine learning, and also problems related to overfitting. These problems related to, so overfitting would be problems related to generalizability, and barren plateau would be problems related to trainability of circuits. And these are closely related to the quantum entanglements and expressibility of the quantum circuits, which means that if the quantum model has excessive levels of entanglement and excessive levels of expressibility, it will cause barren plateaus and overfitting problems, and thereby reducing the generalizability and trainability of the model. So overall, the current status quo of quantum circuits, quantum machine learning, is that there is limited scalability. It is very hard to make large quantum models to process high dimensional complex data. And it is also hard to maintain a feasible level of trainability and generalizability to apply the algorithms for real life usage, practical usage. So that's one of the criticisms that quantum machine learning has been receiving. And what we're trying to do is to overcome this challenge by the multi-chip approach. It is because it is very difficult to create more qubits, create a large model with a stable entanglement. We can make a large ensemble of few qubits for kind of few qubits with stable entanglements. So this is this is an image that I brought from the Japanese cartoon Naruto. So you see this kind of like a gigantic fox monster would be an analogy of a large quantum circuit model composed of a lot of qubits and high connectivity quantum circuits. And this is quite infeasible at the status quo. So what we're trying to do is to make duplicates of small models. So instead of making a large single quantum circuit, we can make small quantum circuits, a lot of them, and then combine them, just like in the photo over there. There's a lot of those the ninja characters Naruto, and they work together to handle a single strong opponent. So it's like that. The main idea of multi-chip ensemble is to create the small quantum circuits, a lot of them composed of small, each of them composed with small qubits, and then we combine the results to handle large high-dimensional complex data sets and tasks. So this is what it is. So instead of making a large quantum circuit with close connectivity among all the qubits, we can make small quantum circuits and then combine them all together. So that's what the idea of multi-chip ensembles is. So it can be seen as the multi-chip ensembles can be seen as dividing a large quantum circuit into multiple smaller, more feasible quantum circuits, and then combine them in after the measurement. And then it can be also seen as creating multiple small quantum circuits and then combining them. So it is the same thing, but we can see it in these kind of two different views, two different perspectives. So the first perspective, we can see that the multi-chip ensembles will have improved trainability, generalizability, and noise resilience. And the second perspective will give us that the multi-chip ensembles will have improved scalability compared to having a large single quantum circuits. Okay, so I will first introduce the advantages related to the first perspective of the multi-chip ensembles. So if we combine a large quantum circuit into multiple smaller circuits, then it will reduce the level of quantum entanglement because there are no entanglements among different chips. Among different small quantum circuits, there are only entanglement, only connectivity possible within the small chips, within the small quantum circuits. So it kind of naturally reduces the quantum entanglement and reduces, thereby reducing expressibility of the entire quantum machine learning model. And this reduced entanglement and expressibility will lead us to improved trainability and generalizability. This is because it has been shown that in these variational quantum circuits in general, excessive levels of entanglement and expressibility leads to barren plateaus and overfitting, which means that similar to the bias variance trade-off in classical machine learning, excessive levels of expressibility increases the error of the model, which means that there's kind of an optimal point, the sweet spot for the quantum circuit model's entanglement, the level of entanglement and expressibility to have the lowest amount of error to have, which means that will be the highest level of generalizability and also the highest amount of trainability of the model. So by reducing the entanglement and expressibility, this multi-chip ensemble approach can better catch the optimal point of the quantum circuit. And this will obviously improve the trainability and generalizability. And also, in variational quantum circuits, noise accumulates as the input data is processed through the unitary gates, which means that there will be a level of quantum error, and the level of quantum error is the amount of deviation that the output quantum state roll out is different. It deviates from the ideal quantum outputs roll out ideal. So in these status quo single chip VQCs, as more unitary gates are in the model, and the more unitary gates that the input data is processed through, there will be more amount of noise accumulated, and it will obviously lead to higher levels of quantum error. But in multi-chip ensembles, there are fewer number of unitary gates and fewer number of noisy channels as well. So there will be a less amount of noise accumulated throughout the model, and this will lead to lower levels of quantum error. So the multi-chip ensembles will have reduced quantum error, and that will obviously mean that it will have higher levels of noise resilience. Okay, and this is the advantage of multi-chip ensembles related to the second perspective of it. So if we the multi-chip ensembles it can be seen as combining multiple quantum circuits, and then we process it to handle high dimensional data, even if we do not use a classical dimension reduction. So on the left image, on the left diagram, we see that because we cannot leverage a large number of qubits, large number of physical qubits right now, we can only use a small quantum circuit with a few qubits. And in order to handle large dimensional data, high dimensional data, we inevitably need some kind of method to reduce the dimension of the classical data, such as a classical encoder layer. But well, this would obviously lead to difficulties in handling high dimensional data without loss of information. But if we use the multiple ensemble approach, even if we have a fewer number of qubits, we can make a small quantum circuit with like 8 qubits as shown in the diagram over here. And then we can just conceptually make an ensemble of it. So we can generate a large quantum circuit model. So if we have 10 chips, 10 quantum circuits, and each individual chip, each individual circuit is just 8 qubits, then it will be 8 times 10. So that will be conceptually equivalent to an 80 qubit large quantum circuit model. So we can handle high dimension data like that, even without dimension reduction. So if I bring the analogy once again about the Narco Ninja, we do not need to make a very large model. We need just one person, one ninja guy, but we can make a lot of clones of him to make conceptually make a large model which can handle very complex data. And so these are the experiments that I've done to prove that these advantages of multi-chip ensembles are true. So I tested MNIST, FashionMNIST, and Cypher. On the presentation here, I only present MNIST results because basically the results were quite similar. The time and space was very limited, but yeah, the results were quite in line with throughout these 3 different data sets. And the dimensionality was for MNIST and FashionMNIST, it was 784 octet flattening, and Cypher 3072. So basically, it works through all the three data sets, which means that the multi-chip ensemble method can process high dimensional data even with thousands of dimensions. And the sample size was 1,000 with train validation and test divisions, and they were flattened and normalized to 0 and 1, and used MNIST loss. Okay, so the model that I used was like this. So first perspective, which means that the multi-chip ensembles can be considered as dividing a quantum circuit into multiple parts with no entanglement between the different chips. So the first analysis would be checking the improvements of multi-chip ensembles that it will have improved trainability, generalizability, and noise resilience compared to the single chip case. And this second model, the second perspective would be that this multi-chip ensemble can be seen as combining a lot of small quantum circuits to generate a large quantum model and process high dimensional data without any dimension reduction. So here, because the MNIST data has 784 dimension, I use 98 chips to conceptually create a large quantum circuit composed of 784 qubits. So it can be, so here I use 98 chips, 98 quantum circuits. Okay, and this is the model performance. So the blue line is the single chip case, the status quo quantum circuits, and by increasing the number of chips, we see that there is performance gains. The loss decreases much faster, and if we use the 98 chip case, an ensemble of 98 chips without any classical dimension reductions, we see that there's a lot of performance gains with very fast convergence to the optimal performance compared to the status quo model. And the classical would be the classical quantum encoder model that just to set kind of a baseline compared to the quantum machine learning models. So that's a classical machine learning just to set as a baseline. And this is the generalizability. So here, compared to the single chip, well, using a dual chip, it may be it showed a bit higher generalization error. So the higher the generalization error, the lower the generalizability. So the lower the better. The smaller the error, the better the model is. But if we look at the 4-chip case, then it shows slightly better performance. And if we check the 98-chip ensemble, it shows a lot of improved generalizability performance. So these results confirm that the multi-chip ensembles approach show better generalizability compared to the conventional single-chip VQCs. And also, this is the results of noise resilience. We see here that compared to single chip, using the multi-chip ensembles significantly improves the noise resilience, which means that it has less amount of quantum error. The model outputs are very close to the model outputs of a noisy quantum circuit is very close to the outputs derived from a noiseless quantum circuit. So it is closer to the ideal output, which means that the model gives more accurate results, even if it is passed through a noisy circuit. So if we use the multi-chip ensembles, there's a very low amount of error. And the interesting thing is that we also compared it with error mitigation method, zero noise extrapolation, which is a very popular error mitigation method often used in quantum machine learning to mitigate the quantum errors. So that's the orange line, and we compared it with the multi-chip ensemble methods. And we found that the multi-chip ensemble methods perform even better than current error mitigation methods. So even if the multi-chip ensemble did not use any error mitigation methods, we did not mitigate it, but it already kind of naturally mitigates the quantum errors if we apply this multi-chip ensemble method to single-chip VQCs.
What kind of error?
Oh, here the noisy quantum circuits. I applied amplitude damping, amplitude encoding noise, and depolarizing noise. So those two types of errors are very commonly occurring in quantum hardware, the status quo quantum hardware. So it will be quite kind of a realistic and practical noise, and the quantum errors would be the resulting quantum errors due to those two types of noise, like noisy quantum channels. So this kind of results show that in multi-chip ensemble model, the quantum outputs were similar to the outputs derived from noiseless quantum circuits, the noiseless circuits that does not have any kind of noise. So it means that it is much more accurate to use multi-chip ensembles compared to using the single chip status quo VQC quantum models. And to kind of wrap it up, the findings show that the multi-chip ensemble QMLs are feasible, and it efficiently distributes the computation across multiple quantum processors, thereby achieving a higher level of accuracy, trainability, and generalizability, and also address challenges of limited scalability in the current QML algorithms. And these imply that the multi-chip ensemble quantum systems will have potential to be applied for large-scale data sets and tasks, which means that QML algorithms could be much more practical and applicable to a variety of different real-life tasks. And it provides a viable framework for improving and enhancing the computational efficiency in quantum machine learning environments. And the future directions for our research would be we can optimize the inter-chip communication to reduce latency. We did not assume we have a lot of communications or differences between each chip, which means that each individual quantum circuit in the chip was set identical. But in the future works, we can make them more heterogeneous and assume more kind of communications between them to optimize the quantum circuit model for each tasks or each data sets. And we can also expand this framework to more complex quantum machine learning architectures. In this study, we just assumed an quantum autoencoder, but we can also apply it for more complicated tasks such as quantum transformers or quantum convolutional neural networks or reinforcement learning models. And we also look forward for investigating more advanced error mitigation techniques to stabilize model performance and also apply for real quantum hardwares such as IBM quantum hardwares. Okay, so that's it, and thank you very much for your listening. Questions or?
It's how does the entanglement arise? If you, when you're trying to manufacture essentially many qubits together, they just naturally get entangled, or is it something else?
Usually it arises from as the data the quantum states are processed through entangling gates. So I will show you using here. So over here, okay. So these individual small boxes, they're quantum gates, and some of the boxes are connected with these lines and dots. So this box connects the first qubit and the second qubit together. So these connected lines indicate that these are entangling gates. So if the quantum states are processed through these entangling gates, they are meant to generate entanglement. But what this, or theoretically speaking, it will create entanglement, but in practice, it does not always create entanglement. Sometimes if there are the level of entanglement could vary, possibly due to parameter initializations or hardware noise, and on and on. There could be many cases. But in theory, entanglement would be created, it would be generated using these entanglement gates.
So, can you say something about your corpora, the test corporation? For the test sets?
The test sets.
Yeah. Data you're using.
The results.
No, the actual data.
Actual data.
So you had a slide where you mentioned two.
Yes.
The data.
This one, MNIST part. What is that?
You mean, I mean the data relating to the data.
Data sets. Yeah.
Oh, the MNIST. So the MNIST and FashionMNIST is the MNIST is the handwritten digits. So so all three data sets are image data sets. Cipher is images of animals, and MNIST and FashionMNIST are images of handwritten data, handwritten digits 0 to 9, and FashionMNIST is clothes like boots, shoes, socks, like jackets, and there. So MNIST and FashionMNIST, it is 28 by 28 pixels, and it is black and white. So if I flatten it, if I flatten it for one dimension, it becomes 784. So in order to process it, you would need 784 qubits, which is infeasible. That's why we have to use classical dimension reduction methods. Using like linear layers, linear neural network layers to reduce the dimension to equal the number of qubits. If that's the like the status quo method used in single chip VQCs, quantum models, and the multi-chip approach that I'm presenting right now is that we can process it without using that kind of classical dimension reductions.
So quantum computers are not throughput machines, right?
Sorry?
So your throughput in a quantum system is fairly limited because of the reconfiguration that you have to do. That my understanding. Where do you see, I mean, realistically, the limits of the data sizes, the data sets that you can work on? You won't be able to, I don't know. Can you train on significantly larger data sets? I guess.
That is the quantum machine learning algorithms applicable for more like diverse, complicated.
Yeah, I mean, this is what the data set here is fairly small, right? In large scale machine learning, we're talking about terabytes, petabytes.
Right. We didn't apply for that. So maybe those applications could be difficult even using this approach. Or at the moment. But if we develop this kind of method even more and more, maybe we can approach that feat that the classical machine learning algorithms are already achieving. So even though there has been a lot of quantum machine learning research, I think it is still a lot to go compared to classical machine learnings. So I think like there will be, I don't know, like several decades of gap between that. So if we do more research, then we will be able to go for terabytes or even more than that.
But it won't be terabytes at that point.
Yeah, maybe, I don't know the
More.
exact metric, but would be like thousands of terabytes.
Well, I guess I'm curious if there was a way to train on a classical computer and do inference on a quantum computer, because the inference, once you have the model and you can fit it on your quantum system, then the inference is fast, right? But for training, that's why I said it's not really a throughput machine.
I think that's a viable approach that we can do like at this moment. And maybe I think it's kind of something that many people are trying to do as well, because of the costs that we face right now. So many models and algorithms that are being developed are hybrid. So like the structure over here uses a classical encoder. So here it is classical encoder because the model that we used was quantum autoencoder. But for example, we can use like a classical transformer or a state space model that has been already trained, like GPTs or so. And then we combine it with quantum models to do inference or like some kind of extra training, and then to get the final results. That would be kind of I think that would be something similar to what you have said. And yeah. Any more questions or like suggestions or anything?
This might just be a clarification question, but like, are these 8-qubit chips, like these single chips that you're using as like one of your sort of test points? Like, is that the limitation for how large of a chip you can build these quantum ML models on, or can you use like 16, 32 qubits?
Like I think the limitation would be like about 32 something,
Okay.
30 something. Like basically like 10 to 12, 20 would be fine. But I for the cipher, I use 12 qubits. So it is possible to make a large model with like about like 20 or 30, even with the current limitations. But it takes much longer time. One of the disadvantages of quantum machine learning algorithms is that they run really slow on classical computers. So the results that I've done was run on classical GPUs, but it takes a significantly longer time than classical models. So the more qubits that I use, the more time it will take. So yeah. And it also leads to a lot of memory costs as well. So if I make a large model of like 30 qubits, then it would take like a tremendous amount of time and require a lot of memory. But of course, the amount of time it takes is quite different on quantum computers, because if it is quantum computers, then it would be light speed. We're using GPUs, that's why it's slow.
So then is it faster or slower you having your 1 8-qubit chip versus having your 98 8-qubit chip ensemble?
Well, it takes the amount of time it takes is longer because obviously you have to run 98 times.
Right.
So it takes longer. But the performance regarding the outputs and generalizability and noise resilience were much better. So which means that it takes long, but it is more accurate and it is more generalizable and also trainable. So it takes quite a long time, but we have to consider this, that we have run we have run these results on classical GPUs. If we were try to run on quantum computers, then this kind of time increase would be negligible. And so which means that we can obtain these kind of trainability, generalizability, noise resilience, scalability improvements, these advantages, even with a negligible increase of time. So it's more beneficial.
That sounds really exciting. Thank you.
You're welcome. Thank you.
There's any questions? Thank you, speaker.